All right, today we're diving into a story that's pretty wild. It's sitting right at the intersection of pure human genius, some seriously deep mathematics, and the incredible power of artificial intelligence.
So here's the central puzzle we're going to unpack. You have a mathematician who comes up with a proof so amazing that it wins her the highest honor in math, kind of like the Nobel Prize. It's celebrated, it's considered a masterpiece. So why on earth did a whole team of experts then spend months teaching a computer how to read it just to check her work? That's the mystery.
To get to the bottom of this, we've got to start with a huge headline that recently made some serious waves in the math and computer science worlds. On that day, a team announced they had finally done it. They had successfully created a version of a world-famous proof that a computer program could read, understand, and then verify as 100% logically sound from the first line to the very last.
Okay, so what was this proof even about? Well, it's a classic problem, but with a serious twist, figuring out the absolute densest way to pack spheres in 8 dimensions. Yeah, try to picture that. It sounds totally abstract, but it actually has real-world implications for things like the error-correcting codes we use everywhere, from space probes to just browsing the internet. The person who cracked it was the Ukrainian mathematician Maryna Viazovska. Her solution was so elegant, so groundbreaking, it won her the Fields Medal back in 2022. The new big deal? Taking her amazing work and translating it so a machine could officially stamp it as perfect.
So, a computer double-checked a genius's homework. You might be wondering, why is that even necessary? Well, that question gets us right to the heart of a huge challenge in the world of modern mathematics. Here's the key difference. A proof written by a person, even a brilliant one, is meant for other human experts, you know? It takes shortcuts, it skips steps that are considered obvious to everyone in that field. It's based on a lot of shared knowledge. A formal proof, though, the kind written for a computer, can't do that. It has to detail every single logical step, no matter how tiny. There is absolutely zero room for ambiguity or error.
And history gives us a perfect example of why this matters so much. Take the famous four-color theorem, the idea you only need 4 colors for any map, so no 2 bordering countries are the same color. In 1879, a respected mathematician published a proof. Everyone bought it. It seemed solid. But a decade later, oops, someone found a hidden flaw. The proof was totally wrong. The theorem did turn out to be true, but it wasn't officially proven until 2005, and guess what? They needed a computer to help them do it.
Now, this isn't a shot at mathematicians at all. The simple fact is that modern proofs can be monstrously long and complex. We're talking hundreds of pages of super dense logic. Expecting any human being to meticulously check all of that and catch every single potential error is just, well, it's becoming an impossible task. Okay, so if human proofs can have these sneaky flaws, and math is getting too complicated for us to check on our own, how in the world do you teach a computer to understand a masterpiece like Viazovska's proof?
The key process is called formalisation, and really you can think of it as a painstaking translation job. It's like taking the shorthand notes 2 expert surgeons use in an operating room and turning them into an exhaustively detailed instruction manual for a robot that has never seen a scalpel before. Every single assumption and tiny action has to be spelled out perfectly.
They do this with special software, in this case, a program called Lean. It works in a few steps. First, mathematicians have to encode the problem in Lean's special programming language. Then, the hard part, they have to fill in all those obvious steps that the original proof just assumes. Finally, Lean's core, its kernel, acts as the ultimate unforgiving referee. It goes through the entire proof line by line and checks if every step perfectly follows the basic rules of logic. If there's one tiny mistake, the whole thing fails.
Now, this incredibly detailed and difficult process of formalization is now getting a massive turbo boost from a new player at the table, artificial intelligence.
And this isn't science fiction. For Viazovska's proof, the team actually used an AI tool they called Gauss. Its job was to help with that translation, suggesting ways to structure the formal proof. And according to one of the project leaders, the AI's help was so good that it literally saved the human team months of tedious work. That's a huge deal.
And Gauss is not alone. There's a whole ecosystem of these AI tools springing up. You've got things like LeanAid, which helps make this whole process more accessible. There's Lean Copilot, which is kind of like an autocomplete for math proofs, suggesting what the next step should be. And then you have the heavy hitters, like DeepMind, building AIs that can generate proofs all by themselves. So the impact of this is spreading across the entire world of math. For students, AI is becoming a kind of on-demand tutor. It's also competing at the highest levels, getting gold medal scores in things like the International Mathematical Olympiad. And for top researchers, it's becoming a true reasoning partner, helping them solve problems and, this is really cool, spotting patterns in data to come up with totally new ideas that a human might have missed.
So this partnership between human intellect and machine reasoning, it's taken us into a completely new and frankly a pretty unpredictable era for discovery. So the big question is, what happens next?
Well, some of the predictions out there are pretty bold. One AI researcher, Christian Szigeti, recently suggested that within a year or so, AI models could become superhuman in almost all areas of math. Now, even if that timeline is a little optimistic, the direction is crystal clear. The pace of change here is just staggering. So, let's bring it all home. Verifying Maryna Viazovska's proof was never about doubting her incredible genius. It was about building a foundation of absolute, undeniable certainty. But it's way more than that. It's really a signpost for the future. We are watching the dawn of a new kind of discovery, where human creativity teams up with machine logic to tackle problems we just couldn't solve by ourselves.
And that leaves us with one final massive thought. We went from using machines as simple calculators to using them as logical partners. The next step could be a machine that can reason in ways we can't even comprehend. And if that happens, what problems that we think are unsolvable today might suddenly have a solution? What entirely new fields of mathematics are just waiting out there to be discovered?